Hi, in this video, we're going to look at some more examples of discrete random variables. My name is Teja, and this is a video series on probability refresher for business analytics and machine learning. So let's start with, so last time we saw the Bernoulli. Let me use the notation x. It was taking two values, any values, let's say 1 and 0, and it will take value 1 with probability, let's say some number between 0 and 1, let's say 0.3. Then it will take 0 with probability 1 minus that, so 0.7. Okay, so these would be the two probability numbers. So this is p of x is equal to 1, and this would be p of x is equal to 0. Okay, so this is a way simple way, a particular way of writing this random variable. Okay, so in this video, let's look at a couple of others. So let's think of so here's one. It's the uniform discrete random variable. Okay, RV is just a short form for random variable. So what is the uniform discrete random variable? So think of in this case, actually, think of let's say our sample space takes the value 10, 20, and 30. Okay, so these are only three possible outcomes in this sample space. Okay, and let the random variable x be the function which takes the value, in this case the outcome, and spits out the outcome itself. So this is a random variable which, in this case, our outcomes are still numbers. So the random variable is going from element of the sample space to a number. So in this case, this is like a very special case type of random variable. So this is a random variable. So let's say in further, let's say that the probability of a particular outcome, for example, 10 is equal to 1/3. Okay, and same thing with probability of 20 is equal to 1/3. Probability of 30 is equal to 1/3. So this is just called the uniform belief, which means that there are three outcomes. So I'll make them, all three of them, equally likely. So 1/3. So I'll divide the probability, which it has to sum to 1 for the sample space into equal parts. So that's why it's 1/3, 1/3, and 1/3. So it turns out that since the random variable is some sort of identity random variable, so probability of x is equal to 10 is also 1/3, and so on. So for the other two as well. So this is a uniform random variable. Okay. Let's also look at the binomial random variable. So binomial random variable x is supposed to represent. So before I tell you what the random variable itself represents, it's a function, right? So let me first define the sample space. The sample space is going to be a set, right, of bunch of outcomes, outcome 1 to outcome, I don't know, let me not index it. How many? Oh, okay. In this case, it's going to be, okay, I don't want to index it. Let me move forward. So let me define that the sample space. So in particular, that sample space is going to be the sequence of outcomes, right? So each outcome, I'm gonna say it's a sequence of heads or tails. So maybe the first outcome is heads, 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 tails, tails, heads, tails. Okay. The next outcome, so which means that I flipped coins these many number of times. In this example, 7 number of times. And the second outcome can be heads, 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 maybe tails, 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 tails. And one of the outcomes can be just tails, 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 tails. So in particular, I didn't index the number of outcomes. The number of outcomes in this case just happens to be the number of sequences. And you saw this before, right? In terms of counting, at each coin flip, I have two choices. So it's 2 to the power 7. That is the number of outcomes. Okay. Which is the size of the sample space. So this is going to be the sample space. And then what is x? X is a function which takes a outcome and spits out a number. And in this case, x is going to represent the number of heads or tails. It's symmetric. I mean, it doesn't matter heads or tails. Number of heads in 7 trials. Okay. 7 or in generally n trials. Okay, so x is a random variable which denotes the number of heads in 7 trials. So this particular random variable is called the binomial random variable. And in fact, it turns out that the probability of x is equal to x, little x, or maybe actually let me use k, little k, is going to be, remember the definition of a random variable, I mean this probability law, it's going to be the set of all outcomes in omega such that there were k heads in n trials. In the above example, it's 7 trials, but in general k heads in n trials. So you can pick all the outcomes, okay, and let's say the so this is a definition of the Bernoulli, and you know how many outcomes are there which can have k heads in n trials. Remember, this was the combination definition from one of the previous videos. This is n choose k, and the shorthand to write the combination is n choose k. Okay, this is nothing but n factorial divided by k factorial times n minus k factorial. Okay, so this is just the number of ways of choosing k trials out of n trials where you would like it to be heads. Okay. Once you do this, then in each such trial where there were k heads, we know that, let's say in in each such outcome where there were k heads, so let's say the first k trials were heads in that outcome. Okay, then for the first k trials to be heads, you have to multiply the probability of being a head. Let's say that's maybe it's a coin, maybe it's fair, maybe it's not, maybe that, let's call that number little p. Okay, little p. Then this p is the probability of heads. Then I'll raise it to the power k because there has to be k heads, and then 1 minus p is the probability n minus k, okay, which is the remaining number of trials where it has to be tails, okay, for that outcome. And there are these many number of such outcomes which have k heads. Okay, so this is the probability of x is equal to k. So this is the derived probability law for the Bernoulli random variable. So note that there is actually nothing special about the few laws that we saw, the uniform, the Bernoulli, or the binomial random variables. In fact, there need not be a name. So need not be a name, a name like Bernoulli or binomial for a random variable x. For example, take this random variable, and I'm going to graphically represent the random variable. So now I'm going to start losing the sight of the sample space. So when I say, okay, let x be a random variable, I'm not really telling you what the sample space originally is. I can directly talk in terms of, okay, if let me x be a random variable, maybe it takes 3 values, which means that maybe x takes value 10, 20, and 30. Then what I'm going to do is I'm going to just think of, okay, what is the probability of x is equal to 10, probability of x is equal to 20, probability of x is equal to 30. Okay, so maybe probability of x is equal to 10 is 1/4, probability of x is equal to 20 is also 1/4, and maybe probability of 30 is equal to 1/2. Okay, so this is the probability. So this is the derived probability law. So this is the PMF. Okay, full description of the PMF, because it's telling me what is the belief that the random variable takes a value 10, 20, and 30, and they sum to 1. So this is a complete picture of a random variable. Note that I did not give a name to this random variable, right? And I guess a small statement about the connection to machine learning is, especially in this field called graphical models, which, for example, is used in text analytics and many other fields, for example, healthcare and so on. You will come across many such random variables. Some of them will be named, and some of them will not be named. But you should be pretty comfortable with thinking about random variables at this point. Thank you for watching.